Good day. My name is Dr. Ngoepe, and I'll be giving a presentation titled on controlling the properties of manganese-rich carbonate precursors using co-precipitation synthesis. I was helped in the work by Dr. Gutierrez and Dr. Croy from Argonne National Labs in Chicago from the Electrochemical Energy Storage Department. So lithium manganese-rich materials have a high capacity of about 250 milliamps hour per gram. They have low cost and safety because of the high manganese content. On the right-hand side is a phase diagram of Li2MnO3, LiMO2, LiM2'O4, which is the spinel phase of the ternary diagram. LMR materials are typically limited by cycle fade and structural stability. In this work, we design and synthesize as well as characterize Ni 0.28, manganese 0.53, cobalt 0.19 carbonate materials. There are three different ways in which a reactor can be operated. In batch mode, which can be thought of as a pot with a closed lid where there are no streams coming in or out. In continuous mode, where both the inlet and the outlet are open, as well as a batch mode where the inlet is open but the outlet is closed. In each case, you're dealing with the volume, quantity, and the rate of the reaction. Now, the reactor itself operates in two modes. Firstly, the semi-batch mode, and secondly, continuous mode. We do not operate the reactor in the batch mode for the sake of these experiments, however. With regards to the problem definition, we are commissioning a 4-liter reactor system. We are using a CSTR or continuously stirred tank reactor as the baseline to develop a 24-hour semi-batch laboratory screening test. Lithium-rich NMCs are synthesized via semi-batch mode, and optimization of reaction time, pH, transition metal to ammonia ratio, temperature, and stirring rate are investigated. So we commission the 4-liter reactor. We then replicate the CSTR conditions for manganese-rich NMC352 carbonate precursor. We generate a set of benchmark materials for lithium and manganese-rich materials. We synthesize and optimize the semi-batch NMC352 CO3 precursor. This is a photograph of the typical 4-liter reactor system. On the left-hand side, we have the overhead stirrer, control box, a pH controller, a stirring controller, and a jacketed 4-liter reactor. On the right-hand side, we have a water bath for controlling the temperature of the system, a gas rotometer, pump feed lines, and solenoidal pumps for pumping the solutions into the reactor. If we were to magnify the reactor part of the system, we are pumping in 2 molar concentration of transition metals, 0.2 to 1 molar ammonia, 2 to 4 molar sodium carbonate or sodium hydroxide, depending on the system. We have baffles installed in the system to control the flow pattern of the material. We have an overhead stirrer with 2 rotors. In each case, we control the reagent concentrations, the pH, the temperature, rotational speed, hydrodynamics, as well as the time. Materials and methods. For the CSTR baseline condition, we have a pH of 8.3, a temperature of 35 degrees Celsius, transition metal to ammonia ratio of 20, a stirring rate of 1000 RPM, residence time of 6 hours, and a total time of 24 hours. For the semi-batch systems, we optimized the pH from 7.5 to 8.7, transition metal to ammonia concentrations of 10 to 25, processing temperatures ranging from 35 to 55 degrees Celsius, reaction times from 6 to 48 hours, and stirring times from 600 to 1400 RPMs. In terms of material characterization, we look at the tap density, particle size distribution, particle morphology, the scanning electron microscope, chemical analysis with ICP, OES, phase composition with XRD, as well as electrochemical testing. Now, with regards to the results, these are the results for the CSTR baseline synthesis condition. We got 57% manganese, 24% nickel, and 19% cobalt. So the manganese content was slightly higher than we expected. However, we did get particles in the right size fraction of about 9.6 microns in diameter for the D50. On the bottom hand side is the XRD pattern of the precursor, which has peaks which are similar to MnCO3. Now, to replicate the conditions in semi-batch mode, we varied the pH from 7.5 to 8.6, and what we saw was that particles became more and more spherical and larger with a higher tap density as the pH increased. We decided to stick to 8.3, which was closer to the type of size we were targeting for the particles. When we optimized the ammonia concentration, we ranged the transition metal to ammonia ratio between 10 to 1 to 25 to 1. There was a complex relationship between the particle size as well as the tap density, reaching a maximum at about 15 and 20 transition metal to ammonia ratios respectively. We decided to stick with the 15 to 1 for the next tests because of the higher tap density. Generally, there was an increase of D50 and tap density with temperature. The particles also became more spherical and less agglomerated as the temperature increased. At 55 degrees, particles are oval shaped and there's very little sign of agglomeration at this temperature. So we selected 55 degrees as the optimal operating temperature. When we varied the reaction time, we found that an increase of reaction time increased the D50 as well as the tap density. However, we're only interested in the 24-hour time, so we just went with the 24 hours. The starting rate was increased from 600 to 1400 RPMs. And once again, there was a complex relationship between D50 and the tap density with the RPMs. The highest tap density obtained was 1.67, which was obtained at 1200 RPM, and particle size, just a D50 of about 22 microns was obtained at that tap density. In terms of electrochemical performance, we found that the effect of transition metal to ammonia ratio showed that at 1.1 lithium to transition metal and 1.25, the 15 to 1 ratio had the highest capacity across the cycle numbers. This was closely followed by the 20 to 1 and then the 10 to 1 ammonia ratio. The efficiencies were in the high 90s for all the products. When the effect of stirring was looked at, we found that the 600 RPM yielded the highest capacity at both the 1.1 lithium to transition metal concentration and the 1.25 lithium to transition metal concentration. This was followed by the 1000 RPM and then the 800 RPM. What we need to point out is that even though the 600 RPM had the highest capacity, in terms of energy density, the 1000 RPM had the highest energy density because of the higher tap density. And this is shown in the first diagram on this slide. The second diagram shows that the effect of energy density on the specific capacity is very dependent on the tap density of the material produced. So even with a material producing 150 milliamps hour per gram, you'd have to have a tap density of at least 2 grams per centimeter cubed at 300 milliamp hour per gram performance in order to get a similar performance. I'd like to thank Argonne National Labs for facilitating the test work, the University of Limpopo, and the Department of Science and Innovation for funding my stay at the Argonne National Labs and for generating necessary support. Thank you.